Hello everyone. In this video, we are going to solve a numerical on the laterally supported beams, which is the second problem in this series. So let's start. Problem statement says that design a laterally supported beam of effective span 5 meter for the following data. So the grade of steel has been given as Fe410. Now the factored maximum bending moment and the factored shear force, which in the previous problem we have calculated ourselves, that has been given directly as 180 kilonewton meter and 220 kilonewton respectively. We need to design the beam, therefore we need to check for the shear force, bending moment, then deflection, then buckling, and after that at the last we will be checking it for the crippling, and our beam should pass all the criteria. Now in the problem it has been said that the deflection is not need to be required for the checking criteria because it is similar to that one, that is WL upon 4 upon 8EI, and it must be less than the value of L by 150. So the same procedure will be there, that's why we will not be requiring to check for the deflection. Everything else will be done here. So since here the load calculation is not to be done, therefore directly we will calculate the plastic section modulus, which will be required us to resist this moment. So the plastic section modulus that will be required, that is denoted by ZPZ, and this will be the required section modulus, and that is given by M upon Fy divided by a factor of safety. Now here if we replace the value of M, that is 180 into 10 raised to the power 6, that will be Newton millimeter, divided by Fy, that is corresponding to the grade of steel that has been given to us as 410. So for that Fy will be 250 megapascal and this gamma M naught value will be 1.1. So from here if we calculate this value ZPZ, that comes out to be 792 into 10 raised to the power 3 cubic millimeter. Now from the special publication number 6 we will calculate, or now from the special publication number 6, that is known as the SP6, from there we will choose a readily available section. So from here we will choose a section. From special publication number 6 we will choose a suitable section that will be having the required section modulus. So if we look at the SP6 table, and from there if we choose a suitable connection member, so the suitable beam section that will be obtained having the same section modulus, that will be ISLB 350, which will be having its strength at 485 Newton per meter. So for this section we will be obtaining the required properties. So ZPZ value that comes out to be equal to 851.11 into 10 raised to the power 3 cubic millimeter. So this is the actual section modulus for this section, however we require the lesser value, that's why it would be appropriate to choose this section. Now the plastic section modulus corresponding to this ISLB section, that is of 350 millimeter depth, that we are obtaining as 851.11 into 10 raised to the power 3 cubic millimeter, which is greater than the required value. All the other properties that will be obtained directly from the Indian Standard Handbook number 1. For example, the thickness of the web section, that is 7.4 millimeter, while the thickness of the flange it is 11.4 millimeter. The corresponding moment of area is 13158 into 10 raised to the power 4 millimeter to the power 4, and the overall depth is 350 millimeter, and the flange width, that is 165 millimeter, and the root radius is 16 millimeter. Now once we are having all the parameters with us, we will calculate the actual depth of the web. So that is calculated by the overall depth minus, because for the I section, let's say this is an I section which is provided by us. So when we are calculating the effective depth for the web section, that is D value, so the thickness of the flange and the root value both are to be subtracted and on both the sides. So this will be D minus 2 into TF plus root radius. So overall depth, that is 350 millimeter minus 2 into 11.4 plus 16. From here we will get the value as 295.2 millimeter, that is the effective depth for the web. Now we will try to classify the section. So the second step will be to classify the section. So for the section classification we will be looking at the certain ratios. So for section classification, So for the section classification, the first ratio is taken as BF by 2 divided by TW. So for the section classification, the first ratio is taken between the flange width and depth. So for the section classification, the first ratio is taken between the width of the flange and the thickness of the flange. So it is given by the ratio of BF divided by 2 to the thickness of the flange. Now the BF by 2 value that we will be calculating here, that is 165 by 2 divided by the thickness of flange, that is 11.4. So from here this value comes out to be 7.23, which is less than the 9.4 value, which is for the plastic section. The another ratio will be taken for the web, that is D by TW ratio, and this D value that is calculated as 295.2, while this TW value, that is the thickness of the web, that is 7.4. So from here we have calculated this value to be 39.9, which is less than the 84 value. Now based upon these two parameters, we will classify this section as the plastic section, because these limits are for the plastic section. So that means our section will behave as a plastic section. So for this section, we will be calculating the shear force, and then we will compare whether it is a high shear case or the low shear case. So for calculating the nominal shear capacity or the design shear capacity, that is denoted by VD, that is given by Fy divided by root 3 into gamma m naught into the area resisting this. So area will be D into TW. So from here this Fy is 250 divided by root 3 into 1.1 into this D overall depth is 350 millimeter into the thickness of web, that is 7.4 millimeter. Now from here if we calculate this value, that will be in Newton, so converting it into directly kilonewton. So from here the value that we are getting, that comes out to be 339.8 kilonewton. Now if we take the 0.6 VD value, because that is to be compared for the low shear or the high shear value, so 0.6 of this 333. So for calculating this 0.6 value for this from this 339.8 value, this is coming out to be 203.98 kilonewton, which is less than the externally applied shear force, which is 220 kilonewton. This was the externally applied shear force, that is 220 kilonewton. So this value is coming out to be less than that value. That means our applied shear force is greater than 0.6 times of design capacity. Therefore, it is a case of high shear, and correspondingly we will be calculating the design capacities. Now we will be calculating the design capacity of the moment. So this MD value, so this design capacity value, that is given by ZPZ into Fy divided by gamma m naught. Now from here this ZPZ will be taken corresponding to the section that we have chosen, that is our ISLB 350 section. So for that it is 851.11 into 10 raised to the power 3 into 250 divided by 1.1. So from here we will be getting the value in Newton millimeter, and converting into kilonewton meter, we will be obtaining this value as 193.43 kilonewton meter. Now this was the actual design capacity when there was no position of the high shear. But since there is a problem of high shear in the beam, because of that some moment will be reduced. There will be a reduction factor in the design capacity. Now for that we need to calculate the section modulus for the section excluding the shear area. So for that what we do, we will obtain the total section modulus minus we will subtract the section modulus corresponding to the shear area, which is given by AW into YW. That means the shear will be obtained in the web area. Now we will be calculating the section modulus for the area excluding the shear area. Now shear will be dominant in this web area, so we will be excluding the shear area, and correspondingly the section modulus will be removed here. Now the overall depth of this section, that was 350 millimeter. Therefore this half of the depth will be 350 by 2, and if we look at the section modulus for this section, it will be the area of web into the centroid position. So this ZBZ value was 851.11 into 10 raised to the power 3 minus this AW value will be 350 divided by 2 into the thickness of the web, that is 7.4 millimeter. Now this YW value is 350 divided by 4, and So we will be subtracting the web area which is dominant in shear. So from the overall section modulus, which is 851.11 into 10 raised to the power 3, we will be subtracting the half the area into its centroidal position, and since it will be revised at the bottom part also, that's why we will be multiplying it with 2. So from here, this value that we are getting, that comes out to be 624.49 into 10 raised to the power 3 cubic millimeter. So this is the actual section modulus which will be calculated by excluding the shear area. Now corresponding to this value, we will be obtaining the MFD value, that is the design moment capacity. So the design moment capacity corresponding to this section modulus, that will be given by MFD, which will be now ZFD into Fy divided by gamma m naught value. Now this ZFD value is 624.49 into 10 raised to the power 3 into Fy is 250 divided by 1.1. So from here, the MFD value that we are counting, that is 141.93 kilonewton meter. Now this is the actual value which is coming for the section. Now we need to check the design value. So for that, high shear gas MDV, that is calculated as the overall value, that is MD value minus a reduction factor is calculated as beta, and the difference between the MD value and MFD value, that is the value which is corresponding to the shear area. So this is the reduction factor for the shear area. So for that we will be calculating this shear factor. So this reduction factor is given by a ratio of 2 into V divided by VD minus 1 its square. So from here we are having all the values with us. So this 2 into this V value was 220, while this design movement of the shear force, while this design shear force was 339.8 minus 1 its square. So from here the value of beta that we are getting, that comes out to be 0.087. So if we place this value here in this equation, so MdV will be obtained as MD, which was 193.43 minus this is 0.087, again 193.43 minus 141.93. So from here, by applying the reduction factor, we have obtained a suitable value which is 188.95 kilonewton meter. Now this MdV value that we have calculated, that must be less than the limiting condition. So this MdV value that we have obtained as 20. So this MdV value that we have obtained as 188.95 kilonewton meter, that must be less than equal to 1.2 times the elastic section modulus into Fy divided by gamma m naught. Now if we replace all the values here, so ZE corresponding to the section that we are having, that is 751.9 into 10 raised to the power 3, Fy is 250, while this gamma m naught value is 1.1. So that means this value should be less than this value, which is 205.06 kilonewton meter. So from here we are obtaining that this MdV value is less than this value. So that's why our design criteria is okay. And this MdV value, which is equal to 188.95 kilonewton meter, and this MdV value, that is the design moment by excluding the shear area, that is greater than the external moment for the factored load, which is 180 kilonewton meter. Therefore our design is okay in case of the bending moment. This was the external bending moment applied, that of 180 kilonewton meter, and this design moment is reduced by a significant amount. As we can see, the earlier value was 193, and because of the high shear present, this value has been reduced to 188, while the earlier value was 193.43. So now we will be checking for the web buckling criteria. So web buckling will be critical at the support. So the next step will be to calculate the web buckling, or to check for the web buckling. For that we need to calculate the ratio that we have not calculated in the previous problem, because that was the cantilever case. Now in this case we will be calculating this D by TW ratio, which is 295.2 millimeter divided by 7.4. From here we get this value as 39.9, which is less than the 67 epsilon. Now this epsilon value is equal to square root of 250 divided by Fy, and since Fy is equal to 250, Therefore, this epsilon value is 1 since Fy is equal to 250. So that means this value of 39.9 is less than 67. Therefore, this d by Tw is okay. Now, since it is a case of high shear, therefore web buckling has to be checked. Now, assuming the bearing length of 100 millimeter, as we were given in the previous question that it was 100 millimeter, here we have assumed that this bearing length is 100 millimeter. Now, correspondingly, we will be calculating the bearing area, which will be this B value plus N1 into the thickness of the web. Now, this N1 will be calculated based upon the depth, overall depth that is present with us. So, N1 will be the overall depth divided by 2. Similarly, here we will be getting this value as 175 millimeter. Now, from all these values, we will be calculating the bearing area, that is 100 plus 175 into 7.4 millimeter. So from here, the bearing area that we are getting, that comes out to be 2035 square millimeter. Now, once we have calculated this bearing area, for that we need to calculate the capacity of the section as a column member. So for that we need the slenderness ratio, and for the calculation of the slenderness ratio, that is equal to effective length divided by the radius of gyration. So this effective length, that is equal to 0.7 times the d value. Now that is equal to 0.7 into 295.2, which comes out to be 206.64 millimeter. And this R value will be calculated based upon the second moment of area divided by the cross sectional area. Now this second moment of area, that is calculated separately as is equal to BTW, it's to the power 3 divided by 12, and from here if we place the value of B as 100 and value of TW as 7.4, then we get the value of I as 3376.87 millimeter to the power 4, while this area will be is equal to B into TW. Now this area will be is equal to B into TW, and if we replace all the values, then we will get this area as 740 millimeter. Now replacing I and A in this equation, the radius of gyration will be obtained. So from here, the radius of gyration that we are obtaining, that comes out to be 2.136 millimeter. So from here, this lambda will be equal to 206.64 divided by 2.136 millimeter. So lambda as a dimensionless number. We are getting as 96.74. Now corresponding to this 96.74, and for the plastic section, the FCD value that we are getting, that comes out to be 111.56 Newton per square millimeter. Now directly multiplying this with the bearing area, we will be obtaining the capacity of the section in the web buckling. So FWB, that is the capacity of the section, that will be AB into this FCD value. So AB that we have calculated earlier, that is equal to 2035 into this stress is 111.6 Newton per square millimeter. So the value that we will be getting, that will be coming out in Newton. So converting into 10 to the power minus 3, so that we have directly the value into kilonewton. From here, the value that we are getting, that comes out to be 227 kilonewton, which is slightly greater than the 220 kilonewton of the shear force. Therefore, the design is okay in case of the web buckling. Now the last step will be for the crippling. Now for the crippling, the check will be performed, and for that again we will be calculating the effective area which will be resisting the crippled load. So for that, again, if there is an I section, therefore we will be taking this value, and now in this case the distribution is at the 1 in 2.5 slope, that is 1 into 2.5 slope. So the width that will be distributed here, that will be TF and R. So that means it will be, end value will be equal to 2.5 times of TF plus R. Now here this 2.5 into TF is 11.4, while this root radius is 16 millimeters. So from here the N2 value that we are getting, that comes out to be 68.5 millimeter. Now the crippling value will be equal to the area, that is B plus N1 at the support into the thickness of the web into Fyw divided by gamma m0. Now this B, that is the bearing length, that was 100, plus this N2 value, that is 68.5, into the thickness of web, that is 7.4. Now Fyw is still 250 divided by 1.1. Now this value that we are getting, that comes out to be 283.4 kilonewton, which is greater than the value of externally applied shear force, that is 220 kilonewton. So that means our section is capable enough to resist the web crippling. So that's how we have performed all the checks necessary for the design of the beam, and that completes the design criteria for the section. Now in the next video, we will look at the design problem of the laterally unsupported beam. So thank you.